Hello everyone, my name is Sean Oliquer, and for my final project I will be discussing graph algorithms and machine learning with graph neural networks. So the main problem statement that I'm looking to tackle in my project is, can I leverage the connections and relationships in a graph to assist with predicting which categories research papers belong to? So essentially, I'm looking to modify existing technologies like classification and improving that with the relational data that inherently exists within relational graph data. And this is especially important to me. Graph neural networks can be generalized for enhancing all classification techniques, not just the specific one that I'm showing here. Particularly, for myself, I work in the aerospace and defense industry, so we're manufacturing a lot of parts, right? We make planes, we make helicopters, the whole shebang. And I work on the quality team, and we're looking to reduce the number of defects that we create, right? A lot of our manufacturing processes are very manual, right? So we're soldering, we're drilling, we're doing things like that. It's not how you would maybe initially think, like in a car manufacturing plant where everything is on an assembly line. There is a lot of manual hands on the part labor. So can we connect a higher level assembly to its lower level assembly and create kind of a relational graph between those assemblies and maybe connect defects from lower level assemblies all the way until kind of the finished product? So I think there's a lot of use cases that I can leverage moving forward. The data set that we'll be using actually comes from Open Graph Benchmark. It's a group within Stanford that allows for the modeling, training, and evaluation of graph machine learning. They're moving it forward with a lot of great benefits, right? It's open source, easily downloaded and split for training within the APIs of the OGB package in Python. The big data scale, right? So we're not just talking about a few thousand nodes or something. We're in the ballpark of 100,000 nodes to 10 million, 100 million edges. So this is, very much big data. And another great benefit is the OGB package has an included evaluator. So you train your model, you load in your model, you train your data, and then you use an OGB evaluator that evaluates all of the models essentially the same if they're all using the API. There's no faking results. There's no, I'm doing 10% better than the rest of the, best in field, right? If the evaluator is consistent, then we're getting consistent testing results on our data set. So the data set specifically, we are using the OGBN archive data set. So it's an open access archive for publishing scholarly articles and papers. That's what archive is, if you haven't heard of it. But the properties of the data set are actually really unique, right? So it's a directed graph of the citation network of archive of all of the computer science archive papers, from existence essentially, up until this data set was captured. I think it was like 2018. And the really unique thing, and the thing that kind of sparked my interest in this data set, is that it was pre-embedded. The inputs, the nodes, are pre-embedded to a 128 dimensional feature vector that was trained on a skipgram model. So it's already embedded. It's kind of ready to run through machine learning, right? You just download that data set, the OGB package transforms it, gets everything kind of set up and ready to go. And we are looking at 4D classes. So each node in our data set, each paper belongs to some subject matter within computer science, right? It concerns artificial intelligence, it concerns operating systems, it concerns robotics, something like that, right? And that's actually what we're going to be trying to predict. And in terms of big data, right, we're looking at 169,000 nodes and 2.3 million edges. So this is something that you're going to need some good hardware to run. So yeah, just keep that in mind as we move forward if you're looking to get into the data. So let's jump into graph neural networks a little bit. If we kind of generalize a neural network, right? a graph neural network is just a neural network that runs on graph data, right? But the unique thing is that graph data can be structured in essentially infinite ways, right? It's if we think of like an image, right, and we break down those pixel values to their left and right and up and down neighbors, right? That's essentially a square graph, right, with 4 cardinal directions that we can traverse that graph over, right? So if we just generalize an image or whatever your data set is, if you have relational data and we generalize that, a graph neural network is a neural network that is just generalized to work on any form of relational data, right? So that's useful because it generalizes loads of data types, right? We can talk about molecules, we can talk about images, we can talk about social networks, right? There's a lot of unique things that we can do with graph data, and the algorithms essentially don't change. We might have to adjust some hyperparameters or something, but essentially the algorithm that you're spitting your data through is going to be consistent. So let's jump into a few graph neural network use cases here. So we can talk about very high level, right, graph level tasks, and this is where we are looking at the entirety of the graph itself, looking for some unique property of the entire graph, right? So if we think about a molecule as a graph, there's oxygen, hydrogen atoms, with various bonds in between them, right? Can we predict whether this entire molecule will bind to a receptor, implicated in a disease or not, right? So we can make predictions based off just the structure of this graph and how everything is connected, right? That is very powerful and something that, if you wanted to make a prediction on an entire data set with traditional machine learning, that might be, I would say borderline very, very difficult, right? Where something like graph neural networks are kind of set up to do things like this, right? Our next use case, right, we can look at node level tasks. So if I want to predict an attribute or an identity of a specific node within a graph, right, that is a person, that is a place, that is something within our graph has some property that we're looking to predict. So if we do like a binary classification, does each person within this karate data set belong to karate club A or B? Do they go to dojo A or dojo B, right? John A or Mr. High, right? Whose dojo do they belong to, right? And this is actually the example that we're going to be using, right? We have all of our nodes, in this case would be papers, and then instead of a binary classification, we actually have 40 classes that we'll be looking at. And the last one that we have is edge level tasks. So in this case, we're looking to predict a relationship between nodes within our graph, right? So if we look at, this graph below, right, we have, if we continue on the karate example from the previous slide, we have 5 different, people or objects within our graph as nodes, right? The one on the bottom would be the mat, and then the other 4 are actually people. So this node is watching, this node is fighting, this node is standing on this node, right? So we're actually looking to predict how those nodes actually interact with each other, right? So some very powerful and unique things that we can do with graphs using graph neural networks. So the particular package that I'm looking to actually dive into is called PyTorch Geometric. So it's built on top of PyTorch, as you might imagine. And the thing I really liked about it is there are great tutorials to kind of get you on your feet. Absolutely compatible with the OGB data loader, right? So you just kind of load in your data, and that's immediately going to break it into training, testing, and validation sets. And then you just essentially feed that into your PyTorch geometric model. So there's some great collaboration there, which was very, very nice on my end. So I also compared this to the DGL, which is a deep graph library, which is another package, and honestly it's a little more deep, which is great if I had more experience in GNNs, but I have some previous experience with PyTorch, so that's kind of why I went down that route. So just a quick demonstration walkthrough here at a very high level, and then I'll jump into the actual training notebook as well, so we can look at some code. But essentially we're going to load the data set, and OGB, like I said earlier, has a fantastic data loader API. So I just called, I'm going to do a node prediction data set, and it's going to be the title of the data set, and then I'm going to transform that into a sparse tensor, right? So looking at this data set, and this is a similar data set, but not the exact one we're using, but these are all of the nodes in our data set just compressed down to 2 dimensions. So you can imagine all of the connections within here, all 2.3 million of them. This is going to get messy very quickly. So just a kind of quick visualization there to kind of set the stage. We're going to create the model, right? And PyTorch, inherits, or our model inherits the PyTorch Graph Sage model, which is just a kind of an advanced graph convolutional network. So we're going to look at one node, and then we're going to convolute, right? We're going to move on to the next node, or all of the next nodes within its, within its neighborhood. This is something called neighborhood sampling. I'm not going to jump too much into that right now, but we do not essentially need the entire graph structure. So if we go, if we go back to that previous slide and we saw all 200, 500, 800,000 nodes that we have in our graph, right? The wonderful thing about GraphSage is that we don't need to load all of those every single iteration or epoch through our training, right? So this actually speeds up considerably the training process, which is very nice. And then we obviously create a training and a test function, and we run that through. And the very fun thing about the OGB package is it comes with an evaluator. So I talked about this earlier, but if we want to evaluate my results versus someone else's results versus everybody else's, well, the wonderful way and the very standardized way of doing that is to have just a standard evaluator from the OGB package, right? So yeah, we see at the very end of our training, all 200 epochs, we get about just under 71% accuracy. And we see something of a confusion matrix here. So along our diagonal, we see something as expected. We see, number 16 is kind of confusing things up with number 24 here, and a few others, but overall looking pretty good and kind of what you would expect from about 70%. So I will go jump to the notebook right now for the last few minutes of this presentation, just so we can actually see the breakdown in the actual code. All right, so yeah, we begin by importing the relative import. So we import Torch Geometric, obviously. Highly recommend CUDA if you have an NVIDIA graphics card. This, brought my training time from about 15 minutes down to like a minute and a half, 2 minutes. So highly, highly recommended. As as we saw earlier, this data is very convoluted, right? And in addition, we load the OGB package and node prediction data sets, and that's where we get the wonderfully packaged data set that we're using. So we saw this, so we're importing the archive data set. We see right here, right, we need an adjacency matrix, right? So we need to know which node has which neighbors so we can connect everything and run our convolutions. And then just for some display purposes, right, we see the number of nodes, the number of edges, and the number of classes. And then the OGB package actually comes with a get index split. So it's going to take the length of your data set, and it's actually automatically going to split your, your data into training, validation, and testing. So it's going to give you the indices of training. So if I just give it the split index at train, it's going to return the indexes of that data set to my device, right? And this is actually part of PyTorch. So this is going to actually send the training data to my GPU. I'm going to next define the model, right? So we have a bunch of important hyperparameters here. And then here is kind of the meat and potatoes of the GraphSage. So we are using the super method here to inherit from the PyTorch module. So we're going to use the Sage Graph Convolutional Network and then append some additional custom layers, right? So we're going to use batch normalization. We're going to add some Sage convolutional layers here as well. And then we're going to define a feed forward function. So this is going to feed everything through the network, right? One node to its neighboring nodes. Here's our adjacency matrix that we're passing in, right? So we're going to convolute the X node and all of its adjacent nodes, right? We're going to run it through our activation function. So this is all very, very familiar. Just again, a generalized version of a neural network for graphs. And then we're going to define an evaluator. So that comes, we're going to evaluate the expected results of the OBG archive dataset. We're going to define a training and a testing function. So nothing super important here. Just taking in that training index, right? The optimizer itself. And then the testing function here is, obviously we're going to have a no gradient because we don't want to update our model during test. We just want to get the test validation and testing accuracy from our split index validation, split index test, and then we're going to run it through the evaluator itself, and then we're going to return those, right? So the model here, we're actually going to call our custom Sage function above, define our optimizer, and then we're going to run it through all of our epochs. So in this case, it's 200 from our hyperparameters above, and then we're going to print them all out here. So we see all 200, nice and messy, but we end up with about 71% accuracy as we saw earlier. We're going to save the model, loading the model for validation and testing purposes if you like. And then we're going to import the familiar confusion matrix. The important thing is that we have to bring all of this stuff back from the GPU. So we have to detach it from the GPU, turn it into a NumPy array, and then down here I'm going to flatten it into a list. And that'll allow us to, obviously compute the accuracy, make sure everything stayed the same from our lists, and then create our confusion matrix and plot it. Thank you very much.